So I've recently written a blog on an interesting aspect of quantum mechanics, and I thought I'll discuss with you. It's related to the the case of hinting towards the discovery of neutrons. Okay, it's a very fascinating kind of a topic, and I would want to actually mention that around in 1920s there was a lot of interest in quantum mechanics. Quantum mechanics, as you know, is a very important part of physics, kind of understanding of the universe, and there were a lot of interesting questions related to what is the constituent of, let's say, nucleus. Okay, now what is nucleus made of? And you would be actually surprised in 1920s. People were thinking that nucleus is still made of proton and an electron. Okay, this is of course not true, because electron is not part of the nucleus, and that has to be actually had to be updated. But that was actually the current understanding, so to speak. So there are a lot of uncertainties, and there are also a lot of questions related to the constituents of both atom and the nucleus. So, for example, the nitrogen 14, the nitrogen nucleus was considered to have, let's say, 14 protons and 7 electrons. That was actually the understanding during that particular time, and people thought that nitrogen nucleus was made of both protons and electrons. There's also another interesting aspect related to this whole kind of thought process during that time, which was a spin statistics. Okay, spin statistics is related to understanding the classification of quantum particles, because they are quantized particles. They have quantized spins, so you can classify them either as Fermi-Dirac statistics or Bose-Einstein statistics. Okay, and these are the two classifications based on the particle, whether they are fermions or bosons in nature. And this creates a very fascinating kind of a process. And as I mentioned, nitrogen was one of the main things which was kind of very interesting, and this was the thought process of having protons and electrons. Now there is something which very interesting happens. uh, Around 1920s, there is a person called as Franco Rasetti. Okay, Franco Rasetti is an Italian postdoc, and he is visiting Caltech. Rasetti is actually an Italian postdoc who is visiting Caltech roughly in the 1929s, and he is motivated by some of the early work of C.V. Raman. Please remember that this is the time, roughly we are talking about 1928 to 29, and 1928 28 is when C.V. Raman's important Raman scattering discoveries happened. And Rasetti is in Caltech. He's motivated. He's reading Raman's paper, and roughly about 1929, he thinks about why not do Raman scattering experiment, and specifically Raman scattering experiment on gases. Okay, and why gases? Because liquid is mainly done by Raman, solid is mainly done by a lot of Russians during that particular time. So gas is a particular component of matter which was not yet studied in significant detail, and therefore he thought, why not take this up as a very important point of looking at this particular experiment. So this motivated him to go forward and set up an experiment. And what he did was he started actually recording Raman spectra from gases like nitrogen, hydrogen, oxygen, and these were the ones which he mainly studied. And in there, what he was looking at is not only just the Raman scattering, but also something called as rotational Raman scattering. And this is a very important point, because in the rotational Raman scattering, what you will find is that there are many interesting issues which are not conventionally available in a gas, or let's say even in a solid, because rotational degree of freedom mainly comes from the fact that if you now have, let's say, a molecule, and if these are representing the atoms of the molecule, you have now degrees of freedom where the molecule can rotate along this axis or perpendicular to this axis. Okay, So there are two axes along which this particular rotation can happen, and this gives a new degree of freedom for one to understand. And that's the current situation which we are looking at. So what Rasetti does is he goes about actually looking at this rotational Raman scattering experiments and tries to understand the characteristics of the rotational Raman spectra of nitrogen. Okay, within the context of the nitrogen, there are a lot of interesting questions. The most important observation what he makes is that the bands which you find in the rotational Raman spectra, this particular band actually has kind of oscillatory signature, meaning some bands are more intense and some are less intense. Okay, and the even bands actually are more intense and the odd bands are not that intense. And obviously the question arises, why is it so? That is because of something called as isomorphism of nucleus. This is a very interesting characteristic of looking at the interaction, because nuclei actually can have something called as para and ortho states. So even for hydrogen, you would have heard para hydrogen and ortho hydrogen. Even for nitrogen, these two states are there. But what happens is that contrary to the convention, the nitrogen's kind of signature was turning out to be such that it was not matching with the prevailing theory of quantum mechanics. However, Rasetti did not really, worry about too much about it. All he did was essentially talk about this particular aspect, and he did mention, okay, there is some very interesting characteristic of the spectral features, etc., etc. Now, there is something which is very interesting which happens. The interesting aspect is that there are two gentlemen, as I've shown here, Walter Heitler and Gerhard Herzberg. They are also postdocs. And by the way, they are postdocs in Max Born's lab. Okay, Max Born, as you probably would be knowing, is a very, very famous physicist, Nobel laureate, optics, quantum mechanics. The interpretation of wave function was actually given by Max Born, by the way. So Heitler and Herzberg, the two H, okay, they were the ones who really were interested in this particular question. They looked at Rasetti's paper and they thought, okay, there is something very interesting in this particular paper. And the interesting aspect is that they went about looking at the nitrogen rotational Raman spectrum from a quantum calculations viewpoint. Okay, Herzberg was a very accomplished molecular spectroscopist, and I've also talked about him in one of my videos in the past. I will link to that too. And Walter Heitler was, of course, one of the greats in quantum theories. These were all early stages. They were all postdocs, you see. They were all very young people. So Heitler and Herzberg, these are all people who are thinking about the problem. So what Heitler and Herzberg do is they took this particular rotational Raman spectral features from Rasetti's paper, and they started asking what is the reason for this kind of observation where the even bands were much more intense. Okay, what they very smartly did was they took this particular nitrogen and they compared that with the hydrogen. So hydrogen was very well known because the hydrogen nuclei is essentially a proton, right? So that particular proton has a spin of half. So this particular spin half particle actually is obeying so-called Fermi-Dirac statistics. So this was very well known. So what they did was they compared the nitrogen with the hydrogen. The prevailing understanding was that nitrogen was also supposed to obey Fermi-Dirac statistics. And hydrogen, of course, anyway obeys Fermi-Dirac statistics. So the features for hydrogen should be similar to nitrogen. But it happened so that it was not the case. There was some discrepancy in this particular viewpoint because they were thinking that this kind of matching is not happening. So there should be some reason why the nitrogen actually is turning out to be completely wrong. and there were questions related to this particular point. So what they did was they went back and checked the quantum statistics for nitrogen. Okay, once they started checking quantum statistics for nitrogen, they found that one would be able to explain the nitrogen spectra, the even bands, the increment, if nitrogen was considered to be a boson. Okay, now if it is considered to be a boson, the nuclei of the nitrogen, specifically the nuclei of the nitrogen, if it is considered to be boson, then everything kind of falls in place, meaning that if one considers the nucleus of the nitrogen to be boson, then they obey Bose-Einstein statistics, and Bose-Einstein statistics can explain the observation of the even bands. This is where I was talking about the even bands, which were actually much more intense. This could actually be explained properly. Now, this is a very interesting characteristics, right? Because earlier the notion was the nitrogen was considered to have this kind of distribution. They thought there is some electron, there is a proton, and this is the constituent of a nucleus of a particular nitrogen nucleus. And this turned out to be incorrect, and therefore they thought that there is some kind of a discrepancy. Okay, and that discrepancy was what Heitler and Herzberg highlighted in this particular paper. So I call them guys from Göttingen precisely for this particular reason, because these people actually are postdocs and really doing very interesting work. And their paper itself was called as "Do Nitrogen Nuclei Obey Bose Statistics?" Okay, that's exactly what they called their paper. And it's kind of very fascinating to learn about this particular paper, and there are many interesting things to learn furthermore. Anyway, I'm linking that particular paper in the blog, so do have a look at them. The other aspect is that the question is why is this particular discrepancy happening? What is the mismatch between the theory and the experiment? In order to address that, we had to wait till 1932. Okay, and what happened in 1932? In 1932, James Chadwick went on to discover neutrons. Okay, neutrons were actually extremely important. This was one of the very important ingredients of a nucleus, which was not kind of known during this particular time. That is quite fascinating. So what people thought was proton plus electron as the constituent of nucleus. What they had to now look at was that the nucleus was made of proton and neutrons. So if you consider neutrons, say for example the nitrogen nucleus, then it contained 7 protons and 7 neutrons. If you consider these two things, then total spin turned out to be, the spin statistics gave that the spin was 1. So if you have spin as 1, this will satisfy the Bose-Einstein statistics. So in contrast, the nitrogen, which was the main element which was compared in the study, happens to be spin half particle, and therefore you would be able to now look at the statistics and discriminate between hydrogen and nitrogen. This is a very crucial aspect because this is kind of hinting towards the presence of the neutrons from a molecular spectroscopic signature. There is something, a very interesting intuition which was developed by the Heitler and Herzberg, and that's an important actually observation. So what do we really learn from all these things? That is always a question we have to ask, right? After all, what is the main lesson you are actually learning in such kind of situation? So as I write in my blog, there are some very important characteristics which you can actually learn. The first and the most important thing is that you would be able to now look at this particular study and draw a conclusion that experiments and theory go hand in hand. That is a very important characteristics. And the second aspect is that it is important for us to perform careful observations and interpretation. This carefulness is very critical and is very important when you're doing science experiments, and these observations and interpretation actually go hand in hand. And the third and very important aspect of which we can learn is that Rasetti, Heitler and Herzberg were all very young people. They were very small researchers, not very well known during that time, but they were postdocs, and you can see they're really doing cutting edge science. And this is a very important aspect for young scientists and postdocs and people who are doing research, even undergraduate students. There is an important lesson to learn from all these things. So finally, the important aspect is you would actually see that we are still discussing something which was happened in 1920s. This is roughly about 100 years since the discovery was made, and we are still discussing, which means that any good work one does, that usually has a very long life. So that is an important thing. So that's one of the reasons why we should also do good work, because the work actually is what will be carried over into the future, and people will start appreciating. Okay, these are the things which I wanted to discuss with you. Okay, and I hope you like this particular video. Do share with people who are interested, and do let me know your comments and what do you think about this particular video. Okay, thank you. Bye bye.